So in last class, we were discussing about polarization. Now we will see some other examples. So let us see next example. Please mute your voice. Please mute your voice. Let us consider a polarized dielectric cylinder. It's a polarized dielectric cylinder. Assume this is XY plane, this is Z direction, its radius is R and length is L. It's a polarized dielectric cylinder and polarization P is given by 5 Z square plus 7 Z cap. Calculate bound charges. You have to find all bound charges. So polarization P is given. You can use this in cylindrical coordinate because it has Z cap component. So this vector is same in Cartesian as well as in cylindrical coordinate. So if polarization is given, what will be surface bound charge? Let us first calculate volume bound charge, rho B. So rho B is minus of divergence P. So that is simply differentiate with respect to Z. So this will be minus 5Z square plus 7. So this will give you minus of 10Z. So volume bound charge density is function of Z. So what will be total volume bound charge? Q rho B, volume integral rho B d tau. So this will give you minus 10Z and d tau is R dr d phi dz. And what will be limit of R? In this case 0 to R, phi 0 to 2 pi and Z 0 to L. So this will give you minus 10 L square by 2. Then you have R square by 2 into 2 pi. So this 2 will cancel out and this will give you minus 5 pi L square. This is the volume bound charge. Now we have to find surface bound charge. So in this case, we have 3 surfaces. This cylinder is surrounded by 3 surfaces. So surface 1 is R is equal to R surface, and on this surface this is N cap. So what will be bound charge on surface 1? R is equal to R. Sigma B is P dot N cap. So P is 5 Z square plus 7 Z cap dot R cap. This N cap is R cap. So Z dot R cap is 0. So in this case, there will be no bound charge on the cylindrical surface. Now you have surface 2. Surface 2 is Z is equal to L plane. And this direction is Z cap. And similarly, surface 3 is Z is equal to 0 and this direction is minus Z cap. this is Z is equal to L. Sigma B is again P dot n cap. So we will get 5 L square plus 7 Z cap dot Z cap. So this will give you 5 L square plus 7. And on surface 3, you have Z is equal to 0. So sigma B is 5 into 0 square plus 7 Z cap dot minus Z cap. So this is minus 7. So these are the surface charge density. So what will be total surface charge on each surface? So you will get 5 L square plus 7 sigma B into dA. dA will be pi r square. dA on this surface will be pi r square. And then 7 in pi r square. So this will give you 5 L square. You will get this will cancel out 5 pi L square r square. So you can see this is total volume bound charge and this is total surround charge. What will be total? Is it? Example. So in this example, you have a dielectric cube. Consider a dielectric cube of side A that is centered at the origin. That carries a polarization P is K position vector R, where K is a constant. Find all bound charges. Again, you have to find all bound charges. So in this case, you have a polarized dielectric cube. Its side is A, and this is centered at the origin. This is X, Y, and Z direction. So you have to find all bound charges in this case. So in Cartesian symmetry, you can write P position vector R as, this can be written as K XX cap plus YY cap plus Z cap. So what will be rho B? Rho B is minus of divergence P. So that will give you divergence of P is 3. So you will get minus 3K. And then what will be Q rho B? Volume integral rho B d tau. So that will give you minus 3K AQ. Because volume integral is, rho B is constant, so d tau will give you volume of the cube. So total volume charge density is minus 3K AQ. Then you have to find surface bound charge. And in this case, there are 6 surfaces, and on each surface we can find bound charge. For example, this surface 1. So this direction is x cap, and opposite to this you have surface 2. So this direction is minus x cap. So surface 1 is, this is centered at the origin. So this plane is x a by 2 and opposite plane is x minus a by 2. So this is x a by 2 plane. And what will be sigma b on this plane? You will get p dot x cap. And just see, p dot x cap will give you kx. And if you put x is equal to a by 2, you will get ka by 2, because x is a by 2. So what will be q sigma b1 on this surface? So that is sigma b dA. Sigma b is ka by 2 and dA is a square. So you will get kaq by 2. So this is total surface bound charge on surface 1. Similarly, on surface 2, x is minus a by 2. So sigma b is p dot minus x cap. So this is minus kx. Again, x is minus a by 2. This is ka by 2. So this will give you q sigma b2 is again k by 2 into a square. So that is kaq by 2. So on both surface, charge will be kaq by 2. Similarly, you can find on surface 3. This direction is plus y cap. Surface 4 minus y cap. Surface 5 z cap. And surface 6 minus z cap. You can easily find on each surface. So surface 3, again y is a by 2. On this surface, p dot y cap, this is ky, that is ka by 2. So this will give you q sigma b3 is again k cube by 2. Multiply with a square d, because sigma b dA. dA is a square. So you will get same. See on 4, fourth is y minus a by 2. Q sigma, this sigma b is p dot minus y cap. This is minus ky and y is minus a by 2. So this is ka by 2. So this will give you q sigma b4 again ka cube by 2. Surface 5 is z a by 2. So sigma b is p z cap. So this will be kz. This is ka by 2. This will give you q sigma b5 is ka cube by 3. And similarly on 6 surface, z is minus a by 2, sigma b p dot minus z cap minus kz, again ka by 2. So on each surface, charge density will be Ka cube by 2, not 3, this is 2. This is Ka cube by 2 on each surface. So you can see on Ka cube by 2, Ka cube by 2, then you have third surface Ka cube by 2, fourth surface, fifth surface, and sixth surface. So what will be total surface bound charge Q sigma b? 6 times Ka cube by 2. So that will be 3 Ka cube. So you can see Q sigma b is plus of this value and Q rho b minus of this value. So what will be total bound charge? Total bound charge is Q sigma b plus Q rho b, and that will be 0. ठीक है?
This 0 is
Clear?
because of uniform polarization, no, sir?
This is non-uniform polarization. Rho b is non-zero. The non-uniform polarization. You can see it is function of R.
Okay, sir.
ठीक है? So if polarization is given, you can find bound charge, and in spherical symmetry we have also calculated electric field. In other symmetry we have calculated the bound charge. ठीक है? Is it clear?
Sir, in non-uniform polarization, rho b is always not equals to 0.
If non-uniform polarization, rho b is non-zero.
And in uniform,
then rho b
always it will be 0.
Uniform, always it will be 0. ठीक है? नोट कर लिया?
Sir, why Q rho b is negative and Q sigma b is positive, sir?
That I have calculated minus divergence P. That value is negative.
So why that negative and that Q sigma b is positive?
I have given this formula because I have also shown you that in different case total bound charge will be 0. So one will be positive, another will be negative. So this is the general relation. If the polarization will get, in that polarization bound charge is, volume bound charge is negative. So this is the general relation. Using this relation, you will get whether it's positive or negative. In general case, you have to use this relation. And I have also shown you why one is positive or another is negative. For example, in a dielectric sphere, if inside charge is positive, volume charge will be negative. If embedded charge is negative, then you will see bound charge will be positive. So that depends on the external field. So for general case, just remember that rho b is minus of divergence P. You will get, if polarization is given, you will get plus minus sign from this relation. ठीक है?
Okay, sir.
In last class, I have shown you why bound on some surface positive charge and volume charge is negative charge. I have given you example. But in general, for all other case, just use this relation. You will get whether bound charge is positive or negative. ठीक है? So till now we have discussed that when polarization is given, how to find bound charge, and if you know bound charge, also calculate electric field due to bound charge. But I told you that is not the actual field. Now we will talk about actual case. What will be the actual field due to polarized dielectric? And for that, we have to modify the Gauss law. You can see, although I have used this relation, for electric field, I have used this relation. E dot dA is Q enclosed by epsilon naught. You know the Gauss law? Let us call it as equation 1. And what is Q enclosed? Q enclosed is total charge enclosed. Total charge means bound charge plus other charge. If you want to use this equation for actual field, you must know what is the total charge enclosed, bound charge plus other charge. So for that, let us take this case. We will talk about Gauss law in presence of polarized dielectrics. So what is the actual case? Let us consider this dielectric. Radius r, and let us place charge q at the center. Again, consider this case. You have a dielectric and charge q is embedded at the center. So what will happen? Because of the external field, this dielectric is placed in an external field of charge q. So dielectric will get polarized and bound charge will develop. So now you have two types of charge. In this case, this external charge, we call it as a free charge. And in this, you have bound charge also. You don't know bound charge. You only know that there will be bound charge, because when dielectric is placed in external field, it gets polarized and bound charge will develop. Now you have to find at point P, r distance away, what will be the actual field. Till now we have calculated field due to bound charge, but now we have to find actual field. So what you will do, let us draw a Gaussian surface. Call this surface as a Gaussian surface.
Sir? Sir?
Yes, yes.
Sir, if the charge Q is not embedded exactly at the center and maybe somewhere else, will the fields vary? Or maybe the bound charges?
Yes, that polarization will be different.
Okay, so bound charges will also be different.
Yes, bound charge will different. That depends on the electric field, how it is placed in an external field. It depends on the electric field. For different electric field, you have different polarization.
Okay.
So now you can see, for actual field, can you use this equation? Because in the Gaussian surface, you know only free charge, you don't know bound charge. So for actual field, you cannot use equation 1 because you don't know bound charge. If you know bound charge, then you can use this equation, because Q enclosed must be free charge plus volume bound charge within the Gaussian surface. So in this particular case, we don't know bound charge, so you cannot use equation 1. And for that, we have to modify this equation. And that modified equation is Gauss law in presence of polarized dielectric. So let us see how to modify this equation to get electron inside. We know that divergence of E is rho by epsilon naught. So rho is volume bound charge density. Volume charge density, rho is the total volume charge density. So it has two parts. one is the bound charge and another is the free charge. You can write in this form because in general we have bound charge density and volume free charge density. F for free charge. Free charge is the any external. So we can write this equation as, what is rho b? You know rho b is, so this equation can be written as divergence epsilon naught E, and this rho b is minus of divergence P plus rho F. So this will be given by divergence of epsilon naught E plus P equal to rho F, or you can see divergence D is rho F. Divergence D is rho F, where D is given by epsilon naught E plus P. Now inside the polarized dielectric, electric field can be represented in terms of D vector, and where D and E are related, D is given by epsilon naught E plus P, polarization P. The differential form, let us see, differential form is divergence D is rho F. So from this equation you will get integral form. Take volume integral of both sides. This is divergence D tau, volume integral rho F d tau, and this is closed D dot dA. This can be written as closed D dot dA, and we can write rho F d tau as free charge enclosed. Must remember this point. Q F enclosed is only free charge enclosed. Free charge enclosed. So you have to distinguish between equation 1 and 2. If only free charge is given and you have to find electric field, you can use this equation. No need to calculate bound charge. But if you want to use this equation for actual field, you must know free charge as well as bound charge. So this is equation 2, Gauss law in presence of polarized dielectric. Now D and E are related. D is epsilon naught E plus P. Let's see relation between D and E. Now polarization of the dielectric material, P is given by epsilon naught chi E into E. E is the external field that is applied. So when you know external field, you can find the polarization, where chi E is the electrical susceptibility of the medium. Susceptibility of the medium. So chi E is known parameter for any material. Its electrical susceptibility is given. So when chi E is given, polarization of material is epsilon naught chi E into E. Epsilon is the permittivity in free space. So now D is given by, how you will write D?
So we
Epsilon
know
naught
this.
E plus P. P. Yes.
So we know the. How do we know the relation between
Epsilon
P
E
and
plus that is the relation that you have to remember. We can derive everything. That you have to remember that P is related with this relation. I am not deriving it.
Okay.
You cannot derive everything. Just remember this relation, how polarization depends. So it depends on the external field, chi E, and then this is the epsilon naught. So D is epsilon naught is common. So you will get 1 plus chi E into E, and we can write D as epsilon 0 epsilon R E, and that will give you epsilon E. So D is, you can see D is epsilon of E, where epsilon is epsilon 0 epsilon R, and what is epsilon R? 1 plus E. So epsilon R is this is defined as dielectric constant of the medium, dielectric constant, or that is relative permittivity. Relative permittivity. So epsilon R is 1 plus chi E. So D is epsilon E, epsilon is epsilon 0 epsilon R. Epsilon R is defined as dielectric constant of the medium or relative permittivity. So when chi E is given, you know it's epsilon R also. Epsilon R or chi E, that is known parameter. So D and E are related with each other. So we have discussed the Gauss law in presence of polarized dielectric, closed D dot D, a free charge enclosed. And you know that D can be written as epsilon E, where epsilon is epsilon 0, epsilon R. Epsilon R depends on chi E. And polarization P is proportional to the applied electric field. And you can remember this relation, epsilon naught chi E into. Now we have to find what will be field. Our actual problem is to find electric field at point P when only free charge is known. So I have discussed that you cannot use equation 1 because you don't know bound charge. So we have derived equation 2. So inside point, you can see this is the polarized dielectric. I have written Gauss law in presence of polarized dielectric. So inside we have a polarized dielectric, you know only free charge. So use equation 2. So for inside point, bound charge is not known. Although you have bound charge, but you don't know what is the bound charge. So you cannot use equation 1. For equation 1, you must know total charge enclosed. So inside point, we will use equation 2. So from equation 2, get mod D into 4 pi r square, and right hand side is free charge enclosed. What is the free charge within the Gaussian surface? That is simply Q. So D is given by Q by 4 pi r square r cap. Now E will be given by D by epsilon. So that is given by 1 by 4 pi epsilon 0 epsilon r Q by r square r cap. Epsilon is epsilon 0 epsilon r. So this is the electric field inside. In a polarized dielectric, you will get electric field. Is it clear? Electric field is D by epsilon in terms of E. Epsilon is epsilon 0 epsilon r. So this is the electric field inside. ठीक है?
Sir, what is this D then physically? If E is the electric field inside, then what is D physically?
D is also the electric field. That is, you have to represent electric field in a polarized dielectric by D vector. Just like E, we represented it in unpolarized dielectric. When you have a polarized dielectric, electric field is represented by D vector. That represents the electric field in a polarized dielectric. In terms of D and E, they are related. You can see D and E are related.
So both of them give the same thing, the same field inside the polarized dielectric.
Which one?
So I cannot understand the difference between E and D that you have written.
Both represent. Just see these equations. I told you both you have to use to find electric field. So when you have unpolarized dielectric, I have used this equation because there is no bound charge. In this case, when you have bound charge, but you don't know bound, you know the actual value of bound charge. So you cannot use equation 1. But when you have a polarized dielectric and you also know the bound charge, you can use equation 1. In this case, when you have polarized dielectric, but you know only free charge, then how to represent electric field? So these are two different equations. One, when total charge enclosed is known, and second equation, when only free charge is enclosed. So you have to represent electric field here in terms of E, here in terms of D. And D and E are related. Just see, I have calculated D and then you can write E here. Both are the electric field.
Okay, sir.
Just different representation, you have different case. In this case, only free charge is known. In this case, total charge is known. So that's why I have used different equation, here in terms of D, here in terms of E. ठीक है?
Yes, sir.
So now we have calculated. Now just see, for outside point, what will happen for outside point when R is greater than R? If you have any point outside the, let's say, R distance away. So in previous case, what will be electric field due to bound charge outside point? I told you that electric field due to bound charge will be 0, because total bound charge enclosed will be 0. But actual field will be non-zero because you have some free charge. You will get field due to this charge. So actual field is non-zero, but field due to bound charge is 0. Now we have to actual field outside. So for outside point, you can use equation 1 as well as equation 2. Both equations are applicable. Just see, because for outside point, it's a free space, so there is no polarization. And if you draw a Gaussian surface, total bound charge is 0, that you know. So you can easily use equation 1 also. So just see, from equation 1, left hand side is mod E into 4 R square 1 by epsilon naught. What is total charge enclosed? Total free charge plus total bound charge. What does this represent? Total bound charge. And you know that total bound charge is 0. So electric field E will be 1 by 4 pi epsilon 0 Q by R square R cap. This is the actual field outside. Field outside due to bound charge will be 0. But actual field is non-zero. This is the case. We can use equation 2 also. Let us see, from equation 2, this epsilon R is 1 plus chi E. From equation 2, you get mod D into 4 pi R square. Free charge enclosed is Q. And outside point, there is free space, so there is no polarization. Polarization P is 0, so this will give you D is epsilon naught E. So what will be electric field? You will get D by epsilon naught. So from this relation, again you will get 4 pi epsilon 0 Q by R square R cap. You will get same electric field. Either you use equation 1 or 2. So for outside point, there is no polarization. In that case, you can use equation 1 or 2. From both relation, you will get same electric field. Just see, because D is epsilon naught E in free space. And here you have directly used equation 1. So both relation will give you same electric field. Is it clear? Is it clear?
Yes, sir. Yes, sir.
Okay. So now let us see last example on polarization. So we will see last example. So again we will use these equations. So first write down, let us write down this example. A spherical conductor of radius A carries a charge Q, it is surrounded by a dielectric material of susceptibility chi e out to radius B. Means from A to B you have dielectric. First part, find electric field in different region. Second part, find the potential at the center. And third part, find the electrostatic energy of this configuration. You have to find, third part is electrostatic energy of this configuration. So now you can see in this example, I have combined conductor as well as dielectric. So you can see you have a spherical, it's a conductor of radius A. So first consider, assume a conductor of radius A and it is surrounded by, this is surrounded by a dielectric material. So this dotted line, this region represents the dielectric and its outer radius is P. Its susceptibility is chi E and this conductor carries charge Q. You can see conductor carries charge Q. So this charge Q will go on the outer surface of the conductor. You know this property. Charge will distribute uniformly over the surface. So you will get E1 is 0. Inside conductor electric field is 0. You have to find E2 in this region and then you have to write E3 outside. You have a conductor that is surrounded by a dielectric material. So in a conductor, electric field will be 0. We have to find E2 and E3. ठीक है? Now you can see this conductor is inside the dielectric and which carries charge Q. So what will happen? This dielectric is placed in an external field of this charge Q. So dielectric will get polarized. It's a polarized dielectric and bound charge will develop. And then you find electric field. So what will be electric field in region 2? So I have written R less than A, field 0. So in region 2, you have to use Gauss law in presence of polarized dielectric. So from A to B, use Gauss law in presence of polarized dielectric. You have to use D dot dA, free charge enclosed. And if you draw a Gaussian surface, you will get free charge enclosed. And then, So from A to B, use this relation. Close D dot dA is free charge enclosed. And then use this D is given by epsilon of E. So that will be epsilon 0 1 plus chi E into E. So if you use this relation, electric field is given by E2. In this medium you will get E2. Let us take it as E2. So that is 1 by 4 pi epsilon 0 1 plus chi E q by r square r cap. You can easily calculate this relation. Electric field in region 2. And in region 3, again you know that total bound charge is 0. So you can use either 1 or 2, both will give you same relation. So E3 can be written as E3, you can easily write E3 is R greater than B. In this region, E3 is 1 by 4 pi epsilon naught Q by R square R cap. So you know electric field in different region. In region 2, you have to use Gauss law in presence of polarized dielectric because you know only free charge. This external charge is the free charge. In region 3, you can use both equation because total bound charge is 0. So this is the first part. You know electric field in different region. Now in second part, if you know electric field, you can find potential at the center. What will be potential? Minus infinity to B E3 dot dl minus B to A E2 dot dl and minus A to 0 E1 dot dl. So this will give you minus infinity to B E3 dot dl is, you will get 1 by 4 pi epsilon naught Q by R square dr and minus A to B 1 by 4 pi epsilon naught 1 plus chi E Q by R square dr, and this term will be 0. So V0 will give you, take Q by 4 pi epsilon naught common. This is 1 by R square is minus 1 by R, so this will give you 1 by B and plus 1 plus chi E. This will give you 1 by B minus 1 by A. This is the potential at the center. If you know electric field in different region, you can find potential at the center. ठीक है? And then last part, electrostatic energy of this configuration. So we have discussed electrostatic energy as epsilon by 2 E square d tau all space, but this is for unpolarized dielectric. So if you have a polarized dielectric, we can just remember this expression in this form. For general case, whether you have polarized or polarized, you can remember in this form. When you have polarized case, for polarized dielectric, dielectrics use D is epsilon E. And when you have unpolarized dielectric, use D is epsilon naught E. So instead of epsilon naught, you will get epsilon. So now we have to calculate electrostatic energy. So just down in region 1, if we write electrostatic energy for epsilon naught you have to use epsilon because D is epsilon E, so you will get epsilon by 2 E square d tau. So this is E2 square. E2 square is A2B E2 square 4 pi r square dr. And third is again epsilon naught 2 B to infinity E3 square 4 pi r square dr. This will give you electrostatic energy. So now you can write epsilon by 2 A to B E2 square is, what will be E2 square? That will give you 1 by 4 pi epsilon naught 1 plus chi E q by r square 4 pi r square dr plus epsilon naught by 2 b to infinity q square by 4 pi epsilon naught r square whole r square 4 r square dr. You know electric field in different region. This epsilon is, this can be written as epsilon naught 1 plus chi e. So you can take q is common by this 4 pi, this will give you 8 pi epsilon naught 1 plus chi e, and this is 1 by r square will give you 1 by a minus 1 by b, and this will give you q square by 8 epsilon naught, and 1 by r square will give you minus 1 by r into 1 by b. So you can take q square by 8 pi epsilon naught common, so that will give you 1 by b plus 1 plus chi e 1 by a minus 1 by b. So this is 1 by r square minus 1 by r. This is the electrostatic energy. Is it clear? This is the electrostatic energy. Whenever you have polarized electron, just replaced epsilon naught by epsilon, and epsilon is epsilon naught 1 plus chi e. You will get the electrostatic energy of the system. Is it clear?
Yes, sir.
If you have any doubt, you can ask.
Yes, sir. Sir,
Bolo.
in region A to B electric field, we have found out that R by capital R cube, but in it Q by R square. Sir, inside the dielectric,
Capital?
small r by capital R cube.
Yes.
And sir, here we are using Q by R square.
And no, क्या कह रहे हो? 1 by?
Sir, inside the dielectric we have found out that for formula small r by capital R cube, and here we are using Q by R square.
Small r by, just tell me, listen what you are saying. 1 small r
by capital R cube.
Small r, no, what?
Inside the,
Why this electric?
Inside the dielectric.
No. This is one in a particular case when it is uniform. I have discussed that case for a unpolarized case. It's a polarized dielectric, so you have to use D dot dA free charge enclosed. Why you are using that equation? It's a polarized case, so you have to use D dot dA free charge enclosed. You have a conductor and that is surrounded by a dielectric. This carries charge Q. So if you have to find electric field, draw a Gaussian surface of S small r and use closed D dot dA free charge enclosed. Use this relation. You will get same equation. Mod D into 4 pi r square into charge Q, and D is epsilon 1 plus E to E. Just see this equation. Yes or no?
Yes, sir. Got it.
Any other doubt?
Excuse me, sir.
Yes.
Second term of potential is limit is B to A.
That is, I think this is
B to A.
A to B. No, this is infinity to B, then B to A, then A to 0. Just see.
Yes, sir.
Yep,
But
this
the second step is
infinity to B, then B to A, then A to 0, because you have to find potential at the center.
the next step.
This is this step.
Yes,
This is
sir.
0. E3. What is E3? 1 by 4 pi epsilon naught q by r square dr.
Yes, sir.
So if you integrate 1 by r square, you will get plus 1 by b term. And in this
Yes.
case, 1 by 1 plus chi e common, q by...
Limit part is
ठीक है?
limit, sir. B to A.
No, this limit is
B to A.
B to A.
Yes, sir. B
Okay.
to A.
So in this case, make this correction. This limit is B to A. Okay, just take it. So you will get here 1 by A minus 1 by B. Just make this correction because limit is B to A. So you will get 1 A minus 1 by B. So just make this correction in potential. I have taken limit from A to B, but correct is B to A. So you get 1 by A minus 1 by B. ठीक है? So that is all about polarization. And in next class, we will talk about electrostatic boundary condition. ठीक है?
Yes,
Okay.
sir.
So in next class, we will see boundary condition. Thank you.
Thank you, sir.
Thank you.
Thank you so